Hey folks, welcome back. And today we are going to start module number 2, and we're going to start talking about binary numbers. So as we saw in the last video, the CPU inside of your computer deals exclusively in binary numbers. So how does everything get converted into binary and back out of binary? And that's what we're going to look at in this module. So the first thing to talk about is you're used to thinking in decimal. Decimal is the name for our current numbering system. And basically, our numbering system is made up of 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Why did they use 10? Well, it probably has something to do with how many digits we generally have. So each one of us uses numbers 0 through 9 to represent quantity. We all know that 1 represents 1, 2 represents 2, and whatnot. But what happens if you need to represent something bigger than 9? Well, the way that we did that in our system is we just use positional notation. The number that's on the right-hand side represents the digits between 0 and 9. The next number over to the left represents the tens, then the hundreds, then the thousands, then the 10,000s, and so on and so forth. So, for example, if I were to try and give you a number such as 3, 4, 7, you understand that that 7 represents just 7. But this 4 really represents 40, and this 3 really represents 300. So you know that what this number actually is 347, which is, of course, what's written on the screen. And it sounds like I'm saying something very obvious, because it is kind of obvious. You're so used to this notation at this point that you don't really think about it. But if I give you a 1, depending on where I put that 1, it has very different meaning. For example, if I say 1, you understand I mean 1. But if I say 1, 0, even though I gave you a single 1, you understand that that means 10. It is 10 times larger than that, simply because of where I put the 1. I put it to the left of another digit. And likewise, if I say 100, you know that that's 100 because it is 2 places over. So this is positional notation, and it's something we use all the time in decimal without really thinking about it. So why is this important with regard to binary? Well, if we were to count up past 9, when we get to 9, we reset the first digit back to 0. And so again, I know this all sounds very obvious, but I promise when we do it in binary in a moment, it's going to seem very less obvious, even though it's the same exact thing. So if I start adding numbers together, the way that it works is we have 0, and then we have 1, and then 2, and then 3, 4, 5, 6, 7, 8, 9. When I reach 9, there's no single digit that I can use to represent the next digit. So what we do is we reset this rightmost digit to a 0, and then we increment, or we increase by 1, the digit to its left. And that gives me 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Again, at 19, I can't increment the digit on the right, so I change it back to 0 and I increment the other digit and we go again. And that gets you to the 20s and then through the 30s and so on and so forth. So each time we run out of a digit, we increment the digit to its left. That's the rule of counting in decimal. Not something you really have thought about, but it is the truth. So this is a very simple set of rules, but it's a very scalable system. When we get to 99, we reset the first digit back to a 0, we increment the second digit. Well, that also has reached the end of its numbers, so it goes to 0 and we add a new digit on front of it. And so we go 98, 99, and then we go to 100, where the third digit, the one furthest to the left, becomes a 1, and the other two digits go back to 0. And then we continue counting. The same happens when we reach 998, 999. Eventually, we can't increment the one on the right, so that pushes the one in the middle over, which pushes the one on the left over, and so we get another digit. Now it's a 4-digit number, which is 1000. And again, 1,000, 10,000, 100,000, a million, and so on and so forth, all the way up. So our system is infinitely scalable. Theoretically, you can represent any number you want. You just keep adding digits to the left until you get to wherever it is that you need to get to. So to phrase this another way, each position in decimal is a power of 10. If you remember powers, 10 to the 0th power is 1, 10 to the first power will be 10, 10 squared is 100, 10 cubed is 1,000. And so the reason that we bring this up is because effectively the first digit is representing the numbers between 0 and 9. The next digit, the second digit, is representing the tens, the third digit is representing the hundreds, and the fourth digit is representing the thousands. And I know I'm saying fourth, but look at how many zeros there are. The power tells you how many zeros are going to be in the number. So each of the numbers in our system is a power of 10. And that's again because we have 10 digits. That's why we chose to do that. Well, computers don't have fingers. They have either a presence of power or an absence of power. And effectively what you can think of that is it's effectively a light switch. When you have a light switch, if you flip it on, there is power. If you flip it off, there is no power passing through, and the effect is that your bulb turns on or off. This is a binary system. There are only two states in which things can be in: on, off. There's nothing in the middle. You can't do some half thing. Don't talk about dimmers. We're only talking about regular light switches that turn on and off. So the switch is either on and electricity is flowing, or the switch is off and no electricity is flowing. Those are the two possible choices in binary. So since computers only run on electricity, they only operate on binary. Or to put it a different way, all computation is done by allowing electricity to flow or not flow. So for the computer to work, everything must be converted to binary. For example, the number 97 happens to convert to this particular binary string. We're going to see how to do that in a moment, but I just want you to be aware that that is what it looks like when you convert decimal to binary. Likewise, characters like A have to be converted to binary, and so the character A actually looks like that in decimal. And everything else that we deal with has to be converted to binary, because that's all the computer deals with. So all music is converted to binary. So when you're listening to Pandora, Spotify, iTunes, Google Music, whatever it is, or YouTube, all of that is a bunch of zeros and ones that are recording how the music sounds. And the details of how all that's done is something you'll get to much later on, but music is converted to ones and zeros. Video is converted to ones and zeros. Your PDFs, your Word docs, your Excel docs, absolutely everything that you deal with in the computer ultimately is converted to a bunch of zeros and ones. The reason that this is important is because this is all the computer can deal with: a sequence of zeros and ones. So to go back to the example of the letters, how did they decide that A was going to be this particular letter? Well, effectively, somebody just came up with a standard. And the initial standard that was used was called ASCII. So ASCII uses 8 bits in order to represent all of the numbers. And the reason that ASCII came around was because in the beginning, computers were mostly dealt with in countries that use the same alphabet or a very similar alphabet to what we are used to in the English alphabet. So when they talked about how many different characters they might have to encode, there's A, B, C, D, E, F, G, all the way up to Z. There's capital A to capital Z, the numbers 0 through 9. And if you look on your keyboard, you've got a bunch of symbols like exclamations and parentheses and at signs and ampersands and stars and square brackets and quotes and single quotes and semicolons and dots and all that kind of stuff. When you add all that together, it came out to about 256 characters, and they made a system that can encode 256 characters. And for many, many years, ASCII was the way that all text was encoded in computers. Until the rest of the world kind of went, excuse me, we're here as well, and we'd really like to be able to encode our languages into computers as well. And it turns out that ASCII can't handle anything outside of the normal character set that we're used to. And what I mean by that is the letters A through Z, and then some small derivatives of that, like the acutes and accent graves and the extra things that are on top of letters in some of the other languages like French and Spanish and German and whatnot. So the rest of the world said, excuse us, but we'd really like to be able to play too. And so eventually we got rid of ASCII for the most part and replaced it with something called Unicode. Unicode uses 16 bits, which means it can handle a lot more different types of characters. And so we're able to encode all the different characters from all of the different languages around the world, including all of the characters that are used in all the different languages. So ASCII was pretty much for English, Unicode is for everybody, and today most encoding of letters is done via Unicode. So again, numbers convert to binary. Letters and characters from every language convert to binary, and everything else also has to convert over to binary. So the next question is, how does all of that work? So we're going to talk about how you count in binary first, and then we're going to look at how to convert things back and forth. The way that you count in binary is the same as the way that you count in decimal, but the problem is in decimal there are 10 characters, and in binary there are only 2. So in decimal, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you increment the next number and you reset the first number and you go again until you get to 19. And then you reset the 9 to a 0, you increment the 1 to a 2, and you're at 20, and you go all the way to 29. In binary, you're going to do that reset a whole lot more often because there's just a 0 and a 1. So we know that if we're going to encode a number into binary, the number 0 is just 0. That's easy. And the number 1 is just 1. Everything is great so far. But the moment that you want to encode the number 2 into binary, you can't do it with those 2 digits. So you had 0, then you had 1. If you want to encode the number 2, because you have run out of digits, you reset the digit back to 0 and you increment the 1 before it. So the number 2 in the number 2 in binary is 1, 0. That's the number 1 and that's the number 0. Okay, so the number 3, well, you can increment the digit. So it's just 1, 1. Great. And now let's talk about the number 4. Well, the first digit, the one on the right-hand side, has reached the end, so it goes to 0. That means that the next digit has to be incremented, but it's also reached the end, so it also goes to 0. And that means that the digit to the left of that needs to be incremented, and so you end up with 1, 0, 0. So 0, 1, those are easy. 2, you now need 2 digits, and it's going to be 1, 0. 3 is 1, 1. And then 4 is 1, 0, 0. 5 is going to be 1, 0, 1. 6 is going to be 1, 1, 0. 7 is going to be 1, 1, 1. And when we get to 8, you're going to have the same problem as before, and you're going to go to 1, 0, 0, 0. All right, and so that's how counting in binary works. It's not actually very difficult. It's just really confusing because you're used to having 10 digits, and now you only have 2 digits. So to think about it another way, you're going to use the powers of 2. So the first position is effectively 2 to the 0, just like it was in decimal. It was 10 to the 0. And then the next one is going to be 2 to the 1, 2 to the second, 2 third, 2 to the third, and 2 to the fourth. Or 2 to the 0, 2, 2 squared, 2 cubed, and 2 to the fourth. And so if you do the math on those, 2 to the 0 is 1, because anything to the 0 is 1. 2 to the first is just 2, because anything to the first is itself. 2 squared is 4, 2 cubed is 8, and 2 to the fourth is 16. And you can go back and double check that. But notice that each time we do the next power, we're doubling the number. And what I mean by that is 1 doubled gives you 2. 2 doubled gives you 4. 4 doubled gives you 8. 8 doubled gives you 16. And 16 doubled gives you 32, 64, 128, 256, 512, 1024, 2048. So binary is actually counting in powers of 2. And this is a very helpful way of converting back and forth between stuff. So anytime you're asked to convert a number into binary, here's what I want you to do. I want you to draw a box that looks like this box. And on the left side, I want you to label the first cell 1, the next cell 2, then 4, then 8, then 16, and keep going as far as you think you might need to go in order to do your conversion. All right, so this is step 1 before they even tell you what number it is that they want you to convert. Start by drawing the box and put the numbers up above it. All right, so now that they've told you that, let's convert our first number from decimal to binary. So we're going to take the number 42, and we are going to convert 42 into binary. So the way this works is I need you to look at these numbers, and I need you to find the largest number that is less than 42. and that turns out to be 32. Because 64 is greater than 42, so it can't be that. So it's the largest number that is still less than 42. And whatever one that is, you're going to put a 1 in that box. All right, so far we have a 1 in the 32 box. The next step is we need to take 32 and subtract it from 42. Now, why are we subtracting 32 from it? So the original number that they were asking us to convert was 42. We have found something that's going to use 32 of that, so we take 32 off it, and that leaves us with 10. And then we repeat the process. Find the largest number that is still less than 10. And the answer to that is 8. So you put a 1 in that box. And then we're going to repeat the process again. I'm going to now, there we go. I'm going to subtract 8 from 10, and that leaves me with 2. Now find the largest number that is less than or equal to that, which is 2. Put a 1 in that box, subtract 2 from it, and you end up with 0. All right, so we have done the conversion at this point. This is all you had to do. All of the remaining cells we're just going to fill with zeros. And the reason we're going to do that is because you still have to record the fact that there was nothing in those boxes. So the conversion of 42 to decimal or to binary ends up being 101010. 42 in decimal is 101010. And if you were to add all of the numbers that have a 1 in them together, you'll end up with the original number that we were converting. 2 plus 8 is 10. 10 plus 32 is 42. And that has to be true, otherwise you did the conversion wrong. Any number that has a 1 underneath it must be added together and end up with the original number. So that's how you can double check that you did it correct. All right, so that's the basics of how we do it. Let's do some practice. So convert each of the following numbers into binary. I'd like you to pause the video, and I'd like you to actually do each of these individually, because this is one of these things that you just need practice on. So I'm going to pause for a moment, and then I'm going to pick up and we're going to work our way through these. Okay, so let's start off with 100. So when we draw out our box, we look for the first number that is less than 100, less than or equal to it. And the answer to that was 64. So we stick a 1 in the 64, and we had 100 at the beginning. Oops. And we're going to subtract 64 from it, and that's going to leave us with 36. All right, so the next thing to do is find the next biggest number that is less than or equal to 36, and that's the 32. So we put a 1 in there, and so we subtract 32 from 36, and that leaves us with a 4. All right, so we find the next largest number that's less than or equal to that number, which is the 4. We subtract 4 from that, and that leaves us with 0. And so we ended up with a 1, 0, 0, 1, 0, 0. And that is the conversion of the number 64 into binary. So the first digit, the first number should have been 1100100. All right, next up, we were supposed to do the number 150. Okay, so in this case, the smallest number, or the largest number that is less than 150 is 128. So we have 150 minus 128, and that's going to leave us with 22. The largest number that is less than or equal to 22 is going to be 16. So we're going to subtract 16 from there, and that's going to leave us with 6. The largest number less than or equal to 6 is going to be a 4. We're going to subtract 4 out of here, and that leaves us with 2. The largest number less than or equal to 2 is 2. Subtract that out, and we get 0. So for 150, the answer was 100101110. That's the encoding of 150. So it's pretty simple. If you follow these rules, you will always get the right answer. All right. Let's take a look. What else did we have? We had 75. And again, if you haven't done this one already, let's take a look at that. So we start off with 75. We draw out our box. and we label all the different parts of this box. So we have 0, 1, oh goodness, not 0. Don't start with 0. Let's start that again. Sorry about that. Doop, 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 doop. 1, 2, 4, 8, 16. And when you're writing these up here, all you have to do is just keep doubling the number. 64. All right, and this would be 128. So 75, the first number that is less than it is that 64. So you take 75 and you subtract 64, and I believe that leaves you with 9. And then you realize that that is not right. 75 minus 64 is actually 11. All right, so the next largest number lower than 11 is going to be 8. So we're going to put a 1 in there. We're going to subtract 8 from here, and that's going to leave us with 3. The next largest number is going to be a 2. So you subtract 2 from that, and that's going to be a 1, and then that's going to be a 1, obviously. So you end up with 1, 0, 0, 1, 0, 1, 1. And that is the answer for 75. Let's double check that I got that right, since I can't seem to do math today. 100, 1, 0. Yes, that looks correct. All right, so let's do 38. So again, we draw our box. We start off with a 1, 2, 4, 8, 16, 32, and 64. All right, 38. So biggest number is going to be 32. So we have 38 minus 32, and that leaves us with 6. Biggest number is going to be 4. Subtract 4, that leaves us with 2. And the biggest number is going to be 2. Subtract 2, that leaves us with 0. So that gives us 1, 0, 0, 1, 1, 0. All right. And then we're going to clear off the screen. I'm going to do number 24. Hopefully you've done these already and you know these answers. If not, you really should do some of them yourself. This is 1, this is 2, this is 4, 8, 16, and 32. All right, so we're doing 24. So the largest number is 16. 24 minus 16 is going to be 8. All right, and then 8 is the next largest number, and that's going to leave you with 0. So we're done. We fill in all the zeros, and we get 1, 1, 0, 0, 0. All right, and now we're down to some simpler ones. The number 3 still works. I'm only going to draw 3 boxes. We have 1, 2, and 4. All right, so we're starting off with 3. Biggest number is going to be the 2. So 3 minus 2 hopefully ends up with 1. Biggest number is going to be a 1. Subtract 1 and you're at 0. And as we know, 3 encodes into 1, 1. And the same thing will be true of 1. We know that that's just going to be 1. All right, so hopefully this makes sense. If you draw out that box, that will always work, and you will be able to always get the right answer. So that's what I would recommend. I will be honest with you, if you ask me to do binary math, that is how I'm going to do it. Those were lots of examples. You can make up your own and you can test them, and you can certainly find calculators on the internet where you can type in a binary number and it will give you the decimal equivalent. So for example, if I say binary to decimal calculator, or sorry, decimal to binary calculator, that's going to give you rapid tables. How about this converter? There's many of them out here. I've never clicked on this, so hopefully it's a good one. So 105, convert, and it gives me back the binary value. So you can make unlimited examples of this. You can test them and make sure that you're getting the right answer. You will have to do this on a quiz or a test. So by all means, make sure that you are familiar with it and you know how to do this, because it is something you are going to have to do for sure. All right, so that is converting from decimal to binary. The next question is, how do you convert in the other direction? What happens if I give you a binary number and I want you to convert that into decimal? Well, it actually works in a pretty similar way to what we did when we were checking whether or not we'd gotten the right answer. So we're given the binary string 11011011. We draw the same exact grid and we fill in 11011011, which is the decimal, no, or the binary number we were given. And then we simply look at the values up above. Anytime there's a 1, we're going to add it. Anytime there's a 0, we're not going to add it. So the answer to this question is whatever 128 plus 64. That looks like 279. So that looks like 192. And then I'm going to add to that 16. And that's going to be 028. And then I'm going to add to that 8. So 208 plus 8 is going to be 216. And I'm going to add to that 2, which is going to be 218. And I'm going to add to that 1, and I get 219. So I believe the answer to this question is 219. Let's see if we're right. And the computer is refusing to move. There we go. Okay, and the answer is yes, indeed, that is correct. So again, all I did was I took the numbers that there was a 1 on, and I added them together. And if you look at the above thing, you can see each of those is just being added together, and I'm skipping all the ones that have a 0. When I add that together, I get 219. So nothing crazy going on there. So converting back from binary to decimal is actually quite easy. All right, so let's take a look at each of these guys. So we have 100100. So that's 0, 0, sorry, I should be putting those in the box, 1001. And so what I need to do is I need to add 32 plus 4 is going to be 36, and that's the answer. So this one is going to be 36. The next one is 1, 4 zeros and a 1. So that's going to be a 1 here, 0. I'm not on pen mode. 1, 0, 0, 0, 0, 1. So that's going to be 37, or 33, I mean, sorry. 32 plus 1 is 33. All right, the next one is all ones, basically. So 1, 1, 1, 1. And that is 3, and then 3 is 6. 1, 2, 3, 4, 5, 6. So if all these are 1s, then it's going to be the sum of all those, and if you add them together, it's going to be 63. Now, you might question, how did I know it was going to be 63 without doing the math? I promise you, if you do the math, that'll come out to 63. And the reason that I knew it is because if the number was 64, it would have been 1 and then all zeros here. So in order for it to be 1 less than that, it has to be 63. That's just a shortcut. If that didn't make sense, don't worry about it. I promise you that one was 63. If you added together, you would have gotten the right answer. All right, next up we have, there's a 1 and a 0, and then a 1 and a 0, a 1, a 0, and a 1. All right, so that's going to be 64 plus 16, which is going to be 80, plus 4 is going to be 84, plus 1 is going to be 85 on this one. And then finally 1, 1, which is going to be 3. All right, so going back and checking all of those, hopefully I got some of those right. All right, and there we go. So 3, 84, 63, 33, and 36 seems to be the right answers. All right, so that's how you convert from binary back to decimal. All right, so if all of that made sense to you, and you have been able to do these conversions, I would strongly suggest that you not listen to the next moment that I'm going to explain. As a matter of fact, you can pretty much skip to when I'm on this slide. All right, so you just tune me out for a moment. If none of that made sense to you, there is a different way that you can do it. And so this is the other option. And one of these will make more sense than the other, so you'll sometimes see this as the answer on the internet. All right, so here's the other method to convert from decimal to binary. We're going to take the number 171 and we're going to try and convert it to to binary. So what we do is we're just going to keep dividing by 2. 171 divided by 2 is 85 and a half. Or to phrase that differently, it's 85 with a remainder of 1. So you record the answer and you record the remainder, just like I did here. And so next up, you take 85 and divide it by 2, and that's 42 with a remainder of 1. And then take 42 divided by 2, that's 21 with a remainder of 0. 21 divided by 2 is going to be 10 with a remainder of 1. 10 divided by 2 is going to be 5 with a remainder of 0. 5 divided by 2 is going to be 2 with a remainder of 1. 2 divided by 2 is going to be 1 with a remainder of 0. And 1 divided by 2 is going to be 0 with a remainder of 1. And then if you read these numbers backwards from bottom to top, you will end up with the correct binary string, 1, 0, 1, 0, 1, 0, 1, 1. All right, so this is another way of doing it. It's using a remainder each time as you go through converting it. They're both valid ways of doing it. One of them will probably make more sense to you than the other. I think you can probably tell by the order in which I presented them which one makes more sense to me, but they do both work, so it's possible to do it either way. All right, so using this new method, if you want to try, here's 3 new numbers for you to convert. So you're going to take 133, you're going to divide it by 2, and then you're going to see what the remainder is. Take the answer that you originally got, divide it by 2, and see what the remainder is, and keep doing that, reading the numbers backwards. If none of that made sense to you, don't worry about it. Just use the other method. Okay, so hopefully you're all back with me. So next off, we're going to talk about the other types of systems that there are. So we've talked about decimal, and we've talked about binary. There are other ways that you can encode information. Another common one that you will see in computers is something called hexadecimal. So in this case, instead of having 2 digits, which is binary, or 10 digits, which is decimal, we have 16 digits, which is hexadecimal. And so in 16-digit math, or in hexadecimal math, you have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have the digits A, B, C, D, E, F. It all works the same way as binary and as decimal. You can represent any number using decimal, binary, or hexadecimal. And to be clear, you could do it with 7 digits, or 9 digits, or 12 digits, or 14 digits, but the 3 most common ones you'll run into are binary, hex, and decimal. Hexadecimal is usually used when you have large numbers that you want to represent, and so they allow you to shrink things down to a smaller number of characters. For example, in hexadecimal, the number FF represents 255. So you're able to represent a pretty big number with just 2 characters. And so that's a kind of a cool thing. So as a result, computers often they don't process in hexadecimal, but they sometimes report things in hexadecimal to us because it's easier to show a larger number without using up a lot of space on the screen. So it's just another system that exists out there. We're not going to spend a huge amount of time on it, but you can certainly convert 18 from binary to hex. You can convert you can convert decimal 18 to binary and then convert it to hex, convert binary 1001001000 to decimal, convert CX or CF to decimal, and convert 101 to hex. And those are just things that you can try. Each of those has their own ability. You're just doing the same thing as you did before. It's just that your chart is going to be slightly different when you're dealing in hex. And you can certainly look up a calculator on the internet to show you the final answer to make sure that you got the right thing. So that's what you're going to do there. So that is converting to binary. Honestly, for this class, the most important thing is that you know how to convert a decimal number to a binary number or a binary number back to a decimal number. We're probably not going to ask you hex numbers on anything. We just wanted you to be aware that they exist. But for the class, you definitely will need to be able to convert binary to decimal, and you definitely will need to be able to convert decimal to binary. Those are the two most important things to get from today's lecture. So that's going to be it for today, and I will see you guys in the next lecture.